Welcome to coinSense. Disclaimer, this video is for informational purposes only and shall not be construed as financial, investment, legal, or tax advice. The sender holds positions in the digital assets mentioned, and shall not be held liable for any errors, omissions, or actions taken based on the information provided herein. Do your own research. Avalanche Platform Whitepaper, the paper outlining the architecture of the Avalanche platform and the various features that make it unique. 2. The engine discussion of the Avalanche platform begins with the core component which powers the platform, the consensus engine. Background, distributed payments and, more generally, computation, require agreement between a set of machines. Therefore, consensus protocols, which enable a group of nodes to achieve agreement, lie at the heart of blockchains, as well as almost every deployed large-scale industrial distributed system. The topic has received extensive scrutiny for almost 5 decades, and that effort, to date, has yielded just 2 families of protocols: classical consensus protocols, which rely on all-to-all communication, and Nakamoto consensus, which relies on proof-of-work mining coupled with the longest chain rule. While classical consensus protocols can have low latency and high throughput, they do not scale to large numbers of participants, nor are they robust in the presence of membership changes, which has relegated them mostly to permission, mostly static deployments. Nakamoto consensus protocols, on the other hand, are robust, but suffer from high confirmation latencies, low throughput, and require constant energy expenditure for their security. The Snow family of protocols, introduced by Avalanche, combine the best properties of classical consensus protocols with the best of Nakamoto consensus. Based on a lightweight network sampling mechanism, they achieve low latency and high throughput without needing to agree on the precise membership of the system. They scale well from thousands to millions of participants with direct participation in the consensus protocol. Further, the protocols do not make use of POW mining, and therefore avoid its exorbitant energy expenditure and subsequent leak of value in the ecosystem, yielding lightweight, green, and quiescent protocols. Mechanism and properties: the Snow protocols operate by repeated sampling of the network. Each node polls a small, constant-sized, randomly chosen set of neighbors, and switches its proposal if a supermajority supports a different value. Samples are repeated until convergence is reached, which happens rapidly in normal operations. We elucidate the mechanism of operation via a concrete example. First, a transaction is created by a user and sent to a validating node, which is a node participating in the consensus procedure. It is then propagated out to other nodes in the network via gossiping. What happens if that user also issues a conflicting transaction, that is, a double spend? To choose amongst the conflicting transactions and prevent the double spend, every node randomly selects a small subset of nodes and queries which of the conflicting transactions the queried nodes think is the valid one. If the querying node receives a supermajority response in favor of one transaction, then the node changes its own response to that transaction. Every node in the network repeats this procedure until the entire network comes to consensus on one of the conflicting transactions. Surprisingly, while the core mechanism of operation is quite simple, these protocols lead to highly desirable system dynamics that make them suitable for large-scale deployment. Permissionless, open to churn, and robust, the latest slew of blockchain projects employ classical consensus protocols and therefore require full membership knowledge. Knowing the entire set of participants is sufficiently simple in closed, permission systems, but becomes increasingly hard in open, decentralized networks. This limitation imposes high security risks to existing incumbents employing such protocols. In contrast, Snow protocols maintain high safety guarantees even when there are well-quantified discrepancies between the network views of any 2 nodes. Validators of Snow protocols enjoy the ability to validate without continuous full membership knowledge. They are, therefore, robust and highly suitable for public blockchains. Scalable and decentralized, a core feature of the Snow family is its ability to scale without incurring fundamental trade-offs. Snow protocols can scale to tens of thousands or millions of nodes, without delegation to subsets of validators. These protocols enjoy the best-in-class system decentralization, allowing every node to fully validate. First-hand continuous participation has deep implications for the security of the system. In almost every proof-of-stake protocol that attempts to scale to a large participant set, the typical mode of operation is to enable scaling by delegating validation to a subcommittee. Naturally, this implies that the security of the system is now precisely as high as the corruption cost of the subcommittee. Subcommittees are furthermore subject to cartel formation. In Snow-type protocols, such delegation is not necessary, allowing every node operator to have a first-hand say in the system, at all times. Another design, typically referred to as state sharding, attempts to provide scalability by parallelizing transaction serialization to independent networks of validators. Unfortunately, the security of the system in such a design becomes only as high as the easiest corruptible independent shard. Therefore, neither subcommittee election nor sharding are suitable scaling strategies for crypto platforms. Adaptive, unlike other voting-based systems, SNO protocols achieve higher performance when the adversary is small, and yet highly resilient under large attacks. Asynchronously safe, SNO protocols, unlike longest chain protocols, do not require synchronicity to operate safely, and therefore prevent double spends even in the face of network partitions. In Bitcoin, for example, if synchronicity assumption is violated, it is possible to operate two independent forks of the Bitcoin network for prolonged periods of time, which would invalidate any transactions once the forks heal. Low latency. Most blockchains today are unable to support business applications, such as trading or daily retail payments. It is simply unworkable to wait minutes, or even hours, for confirmation of transactions. Therefore, one of the most important, and yet highly overlooked, properties of consensus protocols is the time to finality. SNO protocols reach finality typically in less than or equal to 1 second, which is significantly lower than both longest chain protocols and sharded blockchains, both of which typically span finality to a matter of minutes. High throughput, SNO protocols, which can build a linear chain or a DAG, reach thousands of transactions per second, 5,000 plus TPS, while retaining full decentralization. New blockchain solutions that claim high TPS typically trade off decentralization and security and opt for more centralized and insecure consensus mechanisms. Some projects report numbers from highly controlled settings, thus misreporting true performance results. The reported numbers for $AVAX are taken directly from a real, fully implemented Avalanche network running on 2,000 nodes on AWS, geo-distributed across the globe on low-end machines. Higher performance results, 10,000 plus, can be achieved through assuming higher bandwidth provisioning for each node and dedicated hardware for signature verification. Finally, we note that the aforementioned metrics are at the base layer. Layer 2 scaling solutions immediately augment these results considerably. Comparative charts of consensus Table 1 describes the differences between the three known families of consensus protocols through a set of 8 critical axes. Avalanche, Snowman, and Frosty all belong to the SNO family. Please subscribe, like, and share if you enjoyed this video. Thank you for your time.